Okay, great. Well, thank you for having me. I'm Marc Finzi. I'm a PhD candidate at computer science at NYU, advised by Andrew Wilson. Thank you to everyone who's attending and for having me at this seminar. So I'm going to be talking about different ways of embedding symmetries and other high-level structures like conservation laws, energy, momentum, and other constraints into deep learning models for dynamical systems. So to start us off, I want to frame this in terms of a tension that exists between these two different communities, the more traditional, or the deep learning community and the engineering community. So there are parts of these communities, so the reinforcement learning community and the intuitive physics community, as well as the more traditional control systems community within engineering that are tackling overlapping problems, right? So this is, for example, the control of a multi-armed or legged jointed robot, or the, being able to control the joints of a robotic arm to do different tasks, or in general for, designing control systems for very complicated environments, very complicated robots and whatnot. And on the control system side of things, I remember from having once been a pretengineer in undergraduate, the methods that are employed here of you start with, okay, can we identify a dynamics model for this system? Hopefully linear, and if not, maybe we can linearize it and determine the relevant parameters of the system. Whether these are heat capacities or masses or moments of inertia, and we can do that by step responses, or system ID. And so this is on one end of the spectrum in terms of assuming a lot of physical structure about a problem. And this makes sense if we're trying to solve the problem at hand. We should use all this knowledge that we have and all the structure that we can. And of course, there are many, many different methods here. You have your Kalman filters and LQR and PID, and all of these methods, to some extent, use knowledge about these the underlying system that we'd like to control or model. And on the other side of things is the reinforcement learning community and the intuitive physics community that is nested in deep learning, where essentially no physical structure is assumed by these problems. We'd like to control this humanoid robot or this robotic arm, but assume nothing about what these variables or state variables actually mean. What are the joints? How they're related? What all these other properties, and instead just try to learn it entirely from data, whether that be from trajectories or instead observations, reward signals. And this is really quite a dichotomy and a tension that exists between these two different communities. And just to illustrate this fact, to what extent it's not just that the reinforcement learning people don't tend to use these structures, but even they have a distaste for them, right? So if we, for example, on the Mojoko GitHub page for the Mojoko locomotion environments, this OpenAI GitHub, right? There was somebody asking a question about the humanoid robots, and with these large state spaces, of 376 dimensions, and high dimensional action spaces, what do these dimensions actually mean? And the models that people are using in reinforcement learning are just treating this as one big vector with no structure, just as we're going to process this with the multilayer perceptron that is totally agnostic to what these different channels mean. And so when people want to know what these mean, they actually, we see this somewhat, the official response is somewhat patronizing, which is, you don't want to know this unless you're engineering as opposed to learning a solution, right? And that feels quite, and of course, there are many people who are dissatisfied with this answer, because there are many times where actually we do want to leverage this information that we have, right? Or even for, knowing more about the system to know where is it failing, where is it working, why is it working, and all these other things. But the deep learning community comes from a large skepticism of these things and trying to learn as much end to end. So we're looking down upon integrating prior knowledge as feature engineering, or as something that is heuristics and whatnot. But of course, these are essentially and crucially important, and else in other disciplines. And yet, coming from the deep learning, reinforcement learning perspective, these are considered in a very negative light. And there is some question to whether ultimately it is possible that these things could be learned, but and this goes into the debate of what is innate and what is learned in our own evolutionary programming and our learning in the environment, and then also for these other agents. But at the end of the day, that is a trade-off with sample efficiency. So if we are leveraging less information, we can expect to be much less sample efficient and require many more interactions with our environment. So this talk is about methods that are aiming to bridge the gap between these two communities. So assuming some high-level properties about these systems or these Markov decision processes, these RL environments, like symmetries, energy conservation, linear and angular momentum conservation, or Hamiltonian structure. And these are in between these two extremes, where there's something that we understand about the system and we'd like to incorporate it, but we can do it in a way which is agnostic to many of the low-level details of the system, and then apply for a large variety of systems. Okay. So, and then just to illustrate that actually this reinforcement learning community's perspective on this particular issue is a little bit surprising given the success of other methods elsewhere in deep learning. So for example, we have the revolution for images and gridded data with convolutions, and how that came out of the acknowledging the local and translationally invariant or equivariant structure in images. And similarly with graphs, the recent revolution in the last few years about designing methods that can learn from graphs and learn signals on graphs really efficiently. And key to that has been exploiting the actual structure of these graphs and knowing that there is a permutation invariance. It doesn't matter which order we represent the nodes and these other kinds of things. Same thing for sets with deep sets and transformers, point clouds, like shown on the right here, more unstructured data type that have had its own methods, for convolution type things with translation or even rotation equivariance, and other data types as well, molecules, proteins, like the recent breakthrough with AlphaFold. And it would almost be crazy to expect all of these breakthroughs to happen without making the assumptions about the data that these methods do, right? That these methods use knowledge about this data in a way that is beneficial for learning and simplifying the hypothesis space and generalizing. Okay, so clearly this is something that people elsewhere in deep learning use. And I would like to make the analogy that using totally unstructured models like MLPs for these systems of learning the dynamics for some robot, or learning the the policy or the or some other things in reinforcement learning for these robots without using this structure is analogous to trying to make an image classifier while forgetting that it's an image, just pretending that it's just some large vector. And of course, that's much less successful. Okay, so and a big part of this is this idea. So one broadly applicable example of these high-level structures which are applied in many of these different domains that I mentioned, and it is useful for guiding the development of new methods, is the concept of symmetries and equivariance. So there are many different kinds of structures that can exist in our data set that we'd like to capture in our deep learning model. But one of those is a symmetry. And so, and so we can even see that like for array data, if you impose translation symmetry, you get convolution. If you impose locality, you get local convolutions that we're used to. And same thing for graphs, graph neural networks. If you impose the permutation and variance properties, you get graph neural networks and other equivariant models, for example, spherical CNNs working on spherical data, or models that can work with rotations and translations, for example, for molecules. So so I'd like to then go back to thinking about, okay, well, what are some of the relevant inductive biases for learning these dynamical systems that we want to do? So here, let's say we have some, just to give a simple example, we have a pendulum, a triple pendulum, which is swinging around, and we have trajectory data. We have examples of these trajectories, and we'd like to fit a model which can predict the future evolution of this system. Right. So, I'm just going to go over some work in the past few years. So, one useful inductive bias is basically that this system is governed by a differential equation, and that can be encoded into the model through this work called neural ODE, where instead of parameterizing the solution, z of t, the state as a function of time, or even the delta, we're going to parameterize the derivative with respect to time, the dynamics, or in other words, a vector field which says at every point in the phase space, basically describing the state of the system, where does that state go towards? Right, so instead of parameterizing the state, we parameterize the derivatives, and then we can integrate those derivatives with an ODE solver to get back to the states, and then minimize the loss of the predicted trajectories that are rolled out from this ODE solver and the ground truth ones using an L2 loss or something like that, and then just back propagate through to learn those dynamics. Okay. And you can see actually, so, but, for a triple pendulum, something like this system here, if we were to write out these dynamics in terms of these angles, it's actually quite a mess, right? So, just to give us some idea as a simple example of what are we requiring that our neural network learns, it's actually quite a mess. And if you add more links, as a homework problem in undergraduate, how does this, what is the terms for this differential equation, and they grow quite rapidly. Okay. And so then a third kind of level in this level of increasing abstraction is the Hamiltonian neural networks. So this is Gredanis et al. In 2019. And this is basically an additional level on top of neural ODEs, which is saying, if you remember from maybe classical mechanics or theoretical mechanics, there are kind of higher level descriptions of many physical systems in terms of their energy or their Lagrangian. And that these Lagrangians or energy Hamiltonian functions often tend to be simpler in functional form than the underlying dynamics. So by modeling these Hamiltonians, for example, instead of the dynamics, we can reduce some of this burden of learning, simplify the problem, and make learning easier and generalize better. And then we can get back to the dynamics just using, so I'll go into this in a little bit more in a second, but basically the definition of Hamiltonian mechanics. So Hamiltonian mechanics can be written in this way. If we have the state vector z, which includes both the position and the momentum, its derivative with respect to time is just this antisymmetric matrix J times the gradient of the Hamiltonian. And this matrix J is just this antisymmetric matrix here. So basically, we can parameterize the Hamiltonian. We can then take its derivative and multiply by J to get the dynamics. And then we can integrate with the ODE solver to get back to the trajectory, and then minimize the residual between that predicted trajectory and the ground truth. And in this way, we can actually learn a Hamiltonian, an energy function, without having any targets, without having any ground truth observations of the energy, only observations of the trajectory itself. And as you can see for this simple example, moving up this abstraction hierarchy, we have simpler and simpler solutions that the neural network needs to express for this problem, right? This is a much shorter expression, has many fewer, is simpler than this one here, and simpler again than this. Okay. So there are benefits to doing so, both in terms of generalization, but also something which was mentioned in the paper. Oh, right. So let me just reiterate. Right. So this is maybe more typically how you see Hamiltonian mechanics written, which is we have this energy of the system H, Hamiltonian, which is typically the kinetic plus potential energy, and then we can write the derivatives of the state Q and its momentum P, which is related to velocity, in terms of the derivatives of that Hamiltonian. So all you have to do for a system is, if you can write down the Hamiltonian, then you know its dynamics, right? And this is a nice way of looking at things in classical mechanics. But then you can rewrite that if we write this Z as the concatenation of both this position and momentum, then we can write this whole dynamics in a sort of more compact form as just this matrix J times the gradient of the Hamiltonian. Okay, and this idea is essentially used in several different papers with slight variations. So there's this deep Lagrangian neural networks in 2019, which is more focused on the Lagrangian formulation, although they're very similar. Hamiltonian neural networks, which is what I mentioned, and Lagrangian neural networks, which is a slightly more general version of and cleaner version of this line. Right. But they're essentially all the same method, even though they look fairly different in their presentation, but they're essentially talking about the same thing. And one of the advantages that are presented by these methods is that they have, as it seems, so not just better generalization, but also better energy conservation properties. So why is this? So, well, it turns out that this Hamiltonian function that is learned, although it's different from the true Hamiltonian, it is conserved during the rollout from this trajectory, from this learned Hamiltonian mechanics. And to see that, we can just say, okay, what is the time derivative of this Hamiltonian? That is just the gradient dotted with the velocity. And the velocity is just J nabla H. So we can see, because of the antisymmetry of J, this term is 0, right? Because it's anti-symmetric. We just swap this, so that's 0. So what that means is this learned energy function h is conserved during the dynamics, and that seems like a favorable property to have. And the typical motivation for why this is useful is, well, okay, if we have, what happens in a traditional neural network, whether it's modeling the steps or as a neural ODE, is that over time it may lose or gain energy, and this has a qualitatively, large impact on the kinds of solutions that happen over long rollouts. So the stability of long rollouts is not very good, because high energy solutions and low energy solutions or parts of the state space are very different. Versus Lagrangian or Hamiltonian neural networks, where energy is conserved, or at least the learned energy is conserved, and then you have a better, even when you're wrong, right? Like it's harder to be wrong, and even when you're wrong, you're not that wrong because the energy, this important invariant of the system, is preserved. Okay, so it turns out the story is actually a little bit more complicated than is typically portrayed. So as I mentioned, there is a difference between this learned Hamiltonian and the ground truth Hamiltonian. And that difference, although subtle, can be important. So surprisingly, it's the learned energy conservation does not imply a bound on the preservation of the true energy. So this is something that was kind of intuitively obvious, but it turns out it's not true. So this is in a recent paper with my collaborator Nate Groover, deconstructing the inductive biases of Hamiltonian neural networks. Can everyone see this side of the? Okay, are the different images obscuring the vision of these graphs? Okay, let me. Sorry. Right. So if you can see in this graph here, as it turns out, the story is more complicated, and it doesn't seem that Hamiltonian and Lagrangian neural networks a priori are better at conserving the true energy, although they do conserve their own learned energy. And it seems that actually their better energy conservation properties are more due to the fact that they have lower error. And if you have lower rollout error, you can actually have a nice bound on the degree of energy violation. So it seems it's actually almost the reverse of what people originally thought, which is not that these models have better energy preservation and therefore they have lower error, but more like the reverse. For other reasons, they have lower error, and as a result, they have better energy preservation. And you can see on this plot that basically across multiple models, Hamiltonian neural networks and neural ODEs, the energy violation is essentially explained just by a linear relationship with the rollout error if measured in appropriate units. But that's not all is lost. Hamiltonian neural networks and Lagrangian networks do generalize better, and this is something that has been observed in multiple papers and is fairly consistent result. So these inductive biases are helpful, but just not for the reasons that most people think. So why are they helpful? It turns out it's not. So it's not really from energy conservation or even this more subtle property of the symplectic structure that is often people talk about and is a property of these Hamiltonian dynamics. And we don't have to necessarily go into it, but essentially we rule out that this is the explanation for why these models perform better. As you can see by this graph, we develop a way of varying this symplecticity from being exactly symplectic, where the dynamics can be written as some Hamiltonian dynamics, to farther and farther from that. And we can see that actually the error is sometimes positively correlated and sometimes even negatively correlated with having or the rollout error is sometimes negatively correlated with having low symplectic error. So that doesn't seem to be the explanation. And it seems instead to be primarily explained by the second order structure of these models. That they basically implicitly say that there is a second order ODE involved in these for these problems, and that is of the form of this, depending on both the position and the velocity. And then also some other having to do with the simpler parameterization of the dynamics. That's not the only factor, but basically these are the two primary reasons why HNNs and LNNs perform better. Okay. So right now we've talked about some of this prior work, this Hamiltonian neural networks and Lagrangian neural networks, which provide a good example of building in inductive biases to these models. But another good example is that of symmetries, which we talked a little bit about already. But symmetries are not just for images or graphs or point clouds, but they're also for dynamical systems, right? So basically, if we apply some transformation to this dynamical system, we evolve the dynamical system, and then we compare that to first evolving the dynamical system and then applying the transformation, that those two things are equivalent. if there is a symmetry of this system. And so this is true for many different systems. So for example, if we have the spinning top, there's a symmetry about the z-axis, or this, we have the spring pendulum symmetry about the z-axis, or even for, the motion of orbital mechanics, you have our solar system, there are symmetries, rotation, reflection about time, whether time is going forward or backwards, or even translation. You can translate all the elements of the system. And many other systems as well. For our robots, we can swap, one leg for another leg. It's equivalent. We can basically have this reflection symmetry and other kinds of symmetries. And sometimes not just of the dynamics, but of the entire, if we're doing a reinforcement learning problem, or we have some Markov decision process, but the entire Markov decision process has a symmetry. So if we swap not just the states and apply this group transformation to the states, but also to the actions, that we get back the same problem. Okay, and so we can exploit these symmetries by constructing models that also have these symmetries, which are known as equivariant models. So let me just quickly go through that. So what does equivariance mean? So we've kind of been talking about speaking around this, but let's just make some definitions. So we have some symmetry group G, which represents the set of transformations which leave the problem unchanged. So that's G. And we have these group elements. So if we think about what does it mean for a single layer to be equivariant, so let's say we just have a linear layer that maps from one vector space to another vector space, and this could have dimensions C out by C in. Equivariance means that if we transform the input by some representation rho, which is just saying how does this group element act on things, if we transform the input by rho before this matrix W, that's the same as first applying the matrix W and then transforming the output by rho. Now, the output and input representations could be different. This is like, for example, if you have an input which is a vector and the output is a scalar or a matrix, or you have an input which is a graph and an output which is a set, you could have different representations, but the underlying idea is the same. And this also captures invariance as a special case, right? And then the equivariance of the entire network is just the same property, but applied to the network. So if we have a neural network, we apply it on the input X, and then we apply the group transformation, the representation on the output. That should be equivalent to first applying it to the inputs and then applying it to our neural network. So basically these two operations commute. We can either apply the group element first and then the transformation and then our network, or vice versa. And there've been, there's lots of, there's a rich literature on this topic. A paper that really started this all off was this group equivariant CNNs by Cohen et al. 2016. And there are many relevant papers. I'd like to highlight a couple that I contributed to. So there's LeConv, a paper which uses this idea of group convolution plus Monte Carlo sampling and NLP to parameterize the kernel, some details. But basically the motivation there is having a method that could be applied on many different kinds of data and many different symmetry groups simultaneously. And then also more recently, equivariant NLP, which is another general method, but restricted to finite dimensional vector spaces, and where it is a totally different way of basically figuring out all possible equivariant solutions by solving some constraints. And so that's, right. So these are a couple examples, but there are many more, and it's a growing area. So one of the really cool connections here between symmetries in the context of dynamical systems, there is this really cool connection between symmetries and conservation laws, which you may have heard of. It's called Noether's theorem. So if we have continuous symmetries, so not discrete symmetries like the reflection, but continuous symmetries like rotation, translation, these kinds of things, of Hamiltonian or Lagrangian systems, that this is equivalent to conservation laws. For each conservation law, we have a symmetry and vice versa. So what is a symmetry, more precisely defined? So so we can actually just prove this right here. So it's quite simple. So this is Noether's theorem. So continuous symmetry is just the flow of some vector field. So you have some vector field saying that at every point, here is where the points go to. So for example, this vector field here, and that's what we're going to call X. And the Hamiltonian dynamics itself is an example of this. It's just a vector field which says at every point, where does the state go to, right? And the state and velocity, or the state and momentum, right? And so let's say that we're going to also have this additional condition that is technically called symplectic, that basically this symmetry transformation respects the Hamiltonian structure, which is basically just saying that it's like a valid transformation over the coordinates and how that affects its momentum. So that there's a theorem that this implies that this vector field can be written as some as basically this J matrix times the gradient of some scalar phi. Okay, so now we can actually prove that the Hamiltonian H is conserved along the flow of X if and only if and only, so first of all, the Hamiltonian is conserved along the flow of F if and only if it's the derivative of H along the direction of X is 0. So that's just, a fact, so that's this here, right? So let's say that's true, right? So that means that there's a symmetry of H. So we can just write that out, which is just, what is this directional derivative? It's X transpose nabla H. Now, since we know that X transpose, oops, this should be phi, just replace F with phi. So we know that X is equal to J nabla phi. We can just write this out in terms of phi. We can use the fact that J is anti-symmetric. So to get its transpose, pull it out here. And we see that we can rewrite all of this as, rather than the directional derivative of H with respect to X, we can actually write it as the directional derivative of phi with respect to the Hamiltonian dynamics, J nabla H. And so therefore, because this is equivalent to just the time derivative, how does this value change along this direction, along this vector field? This means that, if there's a symmetry of H, if X is a symmetry of H, then time is a symmetry of the conserved quantity, which means that this conserved quantity is invariant. It is conserved. Right, so this is Noether's theorem, and it can be seen just from a little bit of algebra. Right, so therefore phi is conserved along the Hamiltonian dynamics z dot equals J nabla H. So this is really powerful, and let me just give you a couple of examples. Right, so these are classical examples. I'm sure you know them, but I'm just going to review them just in case. So so one great example is translation equivariance in the Hamiltonian or Lagrangian is equivalent to conservation of linear momentum. So how to see this, imagine we have, three-dimensional problem, and we're considering momentum along a particular axis n. So that's this n transpose p. Then the vector field corresponding to n transpose p is this. We can write it out. We can just write that out, using that theorem, and we can write it out, and we see that it's actually just n in the direction of the coordinates and 0 in the direction of momentum. So then the flow along that vector field, which I'm calling H, so flow by parameter lambda along X of particular coordinates just advances the positions by lambda n, and leaves momentum unchanged. So we can see that, okay, if we have this conserved quantity, this is the symmetry, right? So translation corresponds to momentum conservation and vice versa. Here's what this vector field looks like. And similarly, rotation equivariance in H implies and is implied by conservation of angular momentum. So that's a little bit more involved, but basically we just do the same thing. We say angular momentum L is along some direction N is just this Q cross P, which can be written as Q transpose AP for some matrix A, antisymmetric matrix A related to N, which is basically the dual of N. So then we can just do the same thing, and we see that, okay, the vector field that corresponds to this conserved quantity is just this one here. And the flow along that vector field is, so these are matrices A, turns out is just the matrix exponential of these matrices A. And maybe from Rodriguez, this is like a variant of Rodriguez's formula for 3D rotations, and that this is precisely how one would define a rotation about the axis n by an angle theta. So we see that, okay, if we take angular momentum about an axis n, that conservation is equivalent to a rotational symmetry about that axis n. And again, any continuous symmetry is a conservation law for these Hamiltonian systems. Okay, so why is this powerful for Hamiltonian neural networks? We have a Hamiltonian system. Even though it's not the ground truth system, it's some system we're parameterizing. So if our Hamiltonian has symmetries, then our learned dynamics have conservation laws. And this is true even though, this is maybe counterintuitive, but even though the learned Hamiltonian might not conserve the true energy, if it has translation or rotation symmetry, it will conserve the true linear and angular momentum, which is really powerful. So here's an example from one paper, LeConf, where we have Hamiltonian neural networks on some system of interacting particles. And here we can see that basically as we apply symmetries to these networks, if we apply translation symmetry, then linear momentum is conserved. If we apply rotation symmetry, angular momentum is conserved. And if we apply both, then both are conserved. So this is a powerful property that we can imbue into these models, which helps them generalize. And you can actually see improved generalization here. So this is sample efficiency, the size of our data set, and here's test MSE, and that these models outperform other methods like neural ODEs and Hamiltonian neural networks, and even other methods. And then similarly, as another example from our Equivariant MLP paper, is with this mass spring system, which has a rotational symmetry about the z-axis. And we can see if we impose a rotation equivariance about that axis, we get angular momentum conservation for our Hamiltonian neural networks. Right, and you can see, right, so, but that is not, you don't, so that something like 1e minus 4, and of course this depends on the tolerance of your ODE integrator. The better the tolerance it is, the better this will be conserved. Right, but you can see this is not a property of ordinary MLPs. And it's also not a property of neural ODEs, even if they have the symmetry. So you can see here's this gap. We have models that have SO2, which is rotation, O2, which is rotation reflection, symmetries. And when they're Hamiltonian neural networks with those symmetries, they preserve angular momentum. But if they're neural ODEs with those symmetries, while they can improve generalization, they don't conserve angular momentum. All right, so we have this improved generalization properties here as the function of the rollout, as you can see there. Right. So, but then let me just talk about, so that's all well and good. And this is, a really a useful property that can be imbued into these dynamics models, these high-level properties, angular momentum conservation, linear momentum conservation, and to a lesser extent, approximate energy conservation. Oh, that one's a little bit more messy. But there is, and then also just symmetries. Symmetries are helpful in their own right, even if they do not lead to these conservation laws. So even if we don't have a Hamiltonian system, we can still impose these symmetries and expect to get improved generalization. But there's a caveat, kind of the elephant in the room here, which is that symmetries are brittle, and the real world is often more complex than we expect. So in the real world, our assumptions are unfortunately often violated. So, momentum might not be conserved, energy might not be conserved, maybe you have some friction. You might not have the symmetries that are existing in this perfectly clean system. So for example, on the left, ordinary cart pole has a left-right reflection symmetry, but if you just angle it slightly, or if the ground, or if the track is just, has a little bit of bump in it, that symmetry is broken. And same thing with even this example, just this double spring pendulum. If we add some wind or some other perturbations to the system, it will break this rotation symmetry. And same thing for environments like Mujoko, where maybe the dynamics model has a symmetry, but the full environment does not. And this would be because maybe your reward is for moving in a certain direction. And so then moving in that direction breaks the symmetry of the full Markov decision process, the reinforcement learning problem. So it's not an exact symmetry. And this causes a problem for many of these models because a lot of the approaches that we've been talking about so far are not approximate. They're saying, we want exact symmetries, and how do we build them into our networks? And this leads to an inflexibility when accommodating real world data. But this is coming in contrast with the Bayesian perspective, which really says that if we have prior knowledge, it can only be helpful. Prior knowledge should never be a limitation. And the way that this is resolved is just that prior knowledge is not absolute. It is something that can be overruled by enough observations. So even if we believe something a priori to be true, if we have enough observations, we should be able to learn that it's wrong. And the current approaches for embedding symmetries or conservation laws in networks are inflexible in this way. They cannot have this ability to override their initial biases. But the Bayesian paradigm gives us a principled way for doing so. Instead of having a restriction prior, where we place all of our mass on structured solutions, we can instead have a prior which biases us towards structured solutions, but admits the possibility for something more complex and has support for other models. So kind of a loose diagram of this is shown here, where we're trying to illustrate, our prior over different models, and then we can place higher prior mass on the structured solutions that have an exact symmetry or exact conservation law. But we don't need to, it doesn't need to be a restriction prior, right? So we might want still some mass on for solutions that only have approximate symmetries or even no symmetries, so that with enough data, we can overcome this. but have the benefits of both worlds, especially in the cases where we have approximate symmetries. So yeah, so basically how one can do this exactly, I can go into a little bit more detail, but maybe I can just skip through this. Basically, so this is equivariant MLPs, which is one way of making equivariant networks. And how it works is one computes basically the equivariant basis by solving some linear algebra problem, and then parameterizes layers in this basis. Okay, and we'll call that basis Q. And the idea in this paper, residual pathway priors, is that rather than parameterizing the solution in that basis, we should instead impose a prior that has a higher prior variance in that basis, but still some lower, some non-zero prior variance in the orthogonal complement of that basis. And actually, we can view this in a different way if we're using Gaussian distributions as basically the sum of two different layers. One layer, which is an unstructured layer with a low variance, and one layer, which is a very structured layer with a high variance, high prior variance. Okay, so we can do that, and then we can get this ability to accommodate things that we're not expecting and be more flexible. And specifically, this is especially useful in cases where we have approximate symmetries. So here, let's consider three different examples. So one is where we have an exact symmetry. Here we have, so residual pathway priors, I'm going to abbreviate that RPP, and equivariant MLP, or other method, we're going to, with exact symmetries, that's EMLP. So when we have an exact symmetry, EMLP performs great and much better than an ordinary MLP that doesn't have that structure. So these are two different problems. But RPP, which has the bias towards equivariance, also performs very well. So what about in the case where we have only an approximate symmetry? Well, in this case, the MLP does not do well, again, because it has no bias towards even making use of this approximate symmetry, but also the EMLP, the equivariant solution, has trouble. And that's because it is constrained to be exactly equivariant and cannot accommodate anything outside that. So it cannot fully fit the data. Versus our RPP, which can benefit from this inductive bias, but is not constrained by it. Okay, and then finally, we can even accommodate where the user is wrong, where they have some prior knowledge which turns out to be incorrect, such as a misspecified symmetry, right? And in this case, RPP performs as well as or better than the standard MLP, while an EMLP, the equivariant model, fully equivariant model, performs very poorly because the symmetry is not matching the data. Okay, so we can make use of this for the Rojoko locomotion environments. So right, so even though as I mentioned earlier, right, that GitHub issue that nobody knows, essentially the information is lost about what the state spaces and action spaces for many of these robots are. With a little bit of work, one can recover that and identify symmetries, both exact and approximate, in these environments. And actually, if I can, so we made hundreds of videos all about just trying to figure out what each of these different dimensions does, so we can figure out what the symmetries are, and so that you don't have to. All right, let me go back. Right. So, and then incorporating these into reinforcement learning methods, for example, soft actor critic in the Rojoko locomotion environment, we outperform the baseline method that just uses a standard MLP. So here we are using an RPP, or residual pathway prior, with an inductive bias towards equivariance, according to these approximate symmetries that we've identified. And we use that both for the critic and basically the actor and the critic. So the policy network and the value function. And that is shown by this purple curve here. So here are the reward curves. And you can see that with this residual pathway prior, a bias towards symmetries in these problems, we outperform standard soft actor critic, right? One of the closest state-of-the-art method for these kinds of environments. Yeah, and so we outperform them in terms of sample efficiency. This is the number of environment interactions. So we have these different environments. Okay. We also applied this to transition models, where we also saw some benefit, although maybe a little bit milder, but in terms of being able to predict, the dynamics by incorporating these approximate symmetries and how that actually improves rollouts. Okay, so in the last 5 minutes, I'll just go quickly through this. So we've talked about a couple of important high-level properties that can be embedded into these dynamics models and into these RL agents. So that would be symmetries, that would be conservation laws, and Hamiltonian structure. But also there are other kinds of constraints that we might like to impose. So we had another paper exploring this, which is basically that as we go to more and more complex, and especially jointed robots, these configuration spaces get more and more complex. So if we have a pendulum, it's just the sphere. If we have something like a gyroscope, it's actually the space of all rotations. And if we have a multi-jointed robot, it's even more complex. And this actually presents a challenge for models that are learning in those coordinate systems. So, so I'll just go through this quickly, but essentially, if you look at the expressions for the dynamics or the Hamiltonians in systems that have basically a parameterization of these manifolds, so angles or quaternions or Euler angles, these kinds of things, that the expressions are very complex. So multi-link pendulum in 2 dimensions, quite 3D, you don't even want to write it down, it's just a total mess. And spinning tops, likewise. But then actually, if we can instead write them down in Cartesian coordinates, it's much simpler. But the downside of Cartesian coordinates is that Cartesian coordinates do not enforce the constraints. Basically, they do not enforce that we stay on this configuration manifold, right? How do we enforce the fact that these links are of a fixed length, or that this is a top that is spinning, right? And it does not have like the way that that works, or just 3D bodies in general, the constraints that are involved. And so basically, we had a work which is separating out these 2 purposes of the coordinates, which are both trying to express the neural network, basically use the coordinates to express the function that we're trying to learn, whether that be the Hamiltonian or the neural ODE, and also for enforcing constraints. And basically, if we can separate these 2 out and choose what is best for both, so we use Cartesian coordinates to express the Hamiltonian, and then enforce the constraints explicitly, then we can avoid this problem, simplify the learning problem, make it easier. And this is actually going more towards the kind of the simulators that people use in robotics. And it's kind of like halfway between. So no need for Euler angles and gimbal lock and these other kinds of problems for extended bodies. Right, and doing so, right. So basically, there's a little bit of work involved in how do we actually enforce these constraints. And there's actually a really clean way this comes out in Hamiltonian mechanics. Of course, it comes out in other kinds of mechanics too, but basically as a projection to the configuration manifold. So we have you imagine we have the unconstrained vector field saying where everything goes in the dynamics in Cartesian coordinates, and then we just project that onto the configuration manifold. And basically that gives you the correct Hamiltonian mechanics, which is equivalent to if you had just used the intrinsic coordinates of angles, quaternions, or Euler angles, and so forth. Okay, and right, this yields much improved performance. So you see here this constrained Hamiltonian neural network, constrained Lagrangian neural network, and they produce much lower error as integrated over long rollouts compared to Hamiltonian neural networks, neural ODEs, and whatnot, for a large variety of benchmark systems that we experiment with. So you can see these here. And you can check out the paper, right? And so basically yielding rollouts which are predictive for longer time horizons. So that's that. And also with improved data efficiency. So here you can see motion of a double pendulum, which was learned from trajectory data by blue and green constrained models from our method versus purple, like HNN, and yellow, which is a neural ODE. And basically they are able to have predictive rollouts for a lot longer. Yeah, okay. Right, so then, wrapping this up, we can think about many of these different methods as essentially ascending this abstraction hierarchy, so that our model, just in the way that physics gives us a set of abstractions that are lower complexity to be able to explain all the things that we see, we can also use these same tools to simplify the problem that needs to be learned by our neural networks. So instead of the solution or the dynamics, we can go to the Hamiltonian or even the Hamiltonian and Cartesian coordinates, which is more and more abstract representations of the problem, but also lower complexity that we need to learn. And then we can just go back. Okay, and then here, thanks to some of my collaborators here, that worked with me on these projects. So Nick Groover, shout out to them, Greg Benton, Alex Wang, Samuel Stanton, Pavel, and my advisor Andrew, as well as Max Wang. Yeah, so just ramping things up. There are ways of bridging this gap between these two communities of assuming no prior knowledge and assuming entire dynamics models, or entire dynamics models minus a few parameters that need to be fit. And one way of doing that is enforcing these high-level properties like Hamiltonian structure, energy conservation, symmetries, momentum conservation, and constraints. And that these can be imbued into our dynamics models, taking advantage of the structures of the data that they're learning. And that while these one can do that, we can even do it in a way that does not constrain these models, so that it can be viewed as a Bayesian prior rather than a restriction prior. And that symmetries and equivariance are a broadly useful tool, and I encourage you all to check them out. So we have these works, LeCom, BMLP, and of course there are many other really nice works here. So I guess we're going to open up to questions now, I think.
Yeah, we should be able to open the floor to questions now. I think we've gotten all of our audio problems fixed. So sorry about those initially. So you can raise your hand on Zoom, or do the same in the audience, and then just ask questions. So I think Tom had a question. Feel free to unmute yourself.
Yeah, so I have a question, Mark. So that was a very interesting talk. So my question is on high dimensional systems. So you have talked about like ODEs mainly, but in reality, some of these systems will interact with environments that are fundamentally PDEs or like high dimensional systems. So do you have like any insights? How do we incorporate like physical constraints or physical integrations into these like PDE structures?
Yeah. So that's a great question. So, and I think there's even been a little bit of work done on this. So specifically for incorporating symmetries into these, whether they're approximate PDE solvers or other methods relating to PDEs. So basically, that's typically where one discretizes the state space, spatially, and then you have turn the PDE, which is time dependent, into some ODE of some large system. But then you can basically say, okay, on that discretized state space, or on the spatial components, I am going to impose a symmetry there, like translation symmetry, right? And this is something that people have done. This is like, okay, the Navier-Stokes equation, fluid dynamics doesn't matter where the origin is, but also similarly for particle methods. So imposing permutation invariance. So let's say we're using a bunch of particles to represent the solution to a fluid dynamics problem, that we can impose permutation invariance or equivariance by using a graph neural network. So these same ideas are useful there. I think what has been explored less so is this idea of how do we preserve energy and momentum, because oftentimes these systems that we're interested in are don't have this Hamiltonian structure. But I think that there are other ways that one could approach trying to preserve these invariants. But certainly symmetries are like one can use these in all these different areas, even if the system does not have these nice Hamiltonian Lagrangian structures. So that's what I'd say. But it's an interesting research area. I think there's a couple works on it, but there's a lot more to be done, and some exciting ideas there.
Okay, thank you.
Yes. Can you hear me?
Mm-hmm.
Oh, okay. Yeah, I loved your talk. I loved it for many reasons, but one of them is that you sort of called the attention of the audience not to be religious, either modulo dime or NNN, that we have to be open-minded and use anything that we can think of to solve the problem. Now, secondly, I wanted to mention to you that as you started to talk about symmetries, and especially the equivariant models, it occurred to me that the Gestalt, the psychologist Gestalt, and I advise you to look it up. It's very easy reading for you because it's much less mathematical than conceptual. But these guys, this really goes back 100 years, about the 1920s in Germany. they looked at it how people cluster things. You know, what are there any rules that people consider pieces more as a gestalt? That's the word gestalt. And one of the things occurred to me that might be amenable to your equivariant model would be the laws of proximity, minimizing not energy but work. How hard it is to get from place X to place B, given the masses and everything else. So that would correspond to what the Gestalt people talked about, laws of proximity. If you have a shorter distance, you spend less work. You see what I'm saying? If you have a longer distance, you have to work harder. But if you have more regularity, then perhaps you can use that regularity, like the Fourier transform uses regularity to collapse things. So those are my ideas. Wonderful. Thank you.
Yeah, well, thank you. No, I definitely, this does sound like a very interesting area, and I'm interested in reading more about, especially the kind of intuitive physics community that is not the machine learning side, but in terms of understanding how we learn these things, because I think there's a lot of interesting insights to be learned from there. Yeah, and even things like, right, as you say, exploiting these regularities, and how does that impact, how fast does it take us for us to do these certain tasks, and what does that tell us about how we're making use of this?
You
so
see, the Gestalt people have recognized linearity. So if things are grouping more linearly, they would be a preference apparently in the human mind. So also regularity, repetitiveness, and things like that. Look at it; it's an easy reading for you, but the equivariant models with respect to minimizing the work might be okay.
Well, yeah, thank you for that. I think it is, yeah, definitely. And even like the relationships also between things like Occam's razor and, Kolmogorov complexity, and, what is the kind of the minimal description of this problem and how that changes, when you have symmetries or not. I think it's really fascinating, something I'm hoping to learn more about. Thanks.
I have a question. This is Kostas Danielidis. Mark, this was really a wonderful talk. It's really beautiful. And I have followed your work, and you have really done a lot as a junior PhD student. I have a question regarding really getting images as input and going from images which are really where there is a lot of lost information in 2D space to three-dimensional, to groups in three-dimensional space, whether it is SE3 or any other group even might be in space and time. So how can we get from an image, how can we get, what is the best way to get an equivariant encoding on which we could really apply the dynamics that we want also to be equivariant?
Right.
Yeah,
so that's a good question. And I think somewhat of an open question. I mean, of course, one can use the symmetries at the level of the input, of thinking about the symmetries in 2 dimensions of the image rather than on the underlying, latent 3-dimensional space. So that is one thing that people have done and can do. But then, in terms of, okay, we understand that there are these symmetries in 3-dimensional space that is really what we care about. I think that is something that is more challenging that, some people have some ideas for, but is somewhat still unsolved. So, I mean, of course, if you have a method that is some extracting from this image, more like tabular description of the state of the system, then you can do that. Or you might even be able to do something like, you have some autoencoder that is going to some lower dimensional space, and then basically you're saying, okay, I just have some representation of the symmetry group, and you're being more than agnostic about what these exactly mean, but you have some representation that represents some symmetry there. So I think that there are some ideas here, but there isn't a really a good answer, or comprehensive answer yet to this question. But it's something that is interesting, and I'd like to see more work tackling that problem.
Like everyone said, this is a really interesting topic and a great talk. Thank you. My question is, if we assume that the system we're working with is Lagrangian or Hamiltonian, and that we have some, prior on a symmetry, we know how to transform sort of the inputs and outputs of that system according to that symmetry, kind of more in the style of like classical reduction theory, like geometric mechanics. So what is the advantage of like baking symmetry into the neural network component versus like essentially applying that symmetry transformation, before entering the neural network and then, sort of reversing it afterwards. My first thought might be that maybe this is where the Bayesian perspective comes in, that it's a more flexible way of embedding it. But I could also imagine you could have sort of a symmetry enforced, black box and another one that you sort of weight separately. So like, what is the advantage of baking that directly into the neural network instead of applying that constraint like before and after?
Yeah, so I think it basically is an advantage in terms of and allowing a richer expression of functions. So this is kind of like the difference between invariant models and equivariant models. Or a good example is actually going back to sort of more classical computer vision examples and imagining what would happen if we did this there, right? So one example is what happens in an image if we, rather than using a convolutional model, which is inherently translationally equivariant and then pooling at the end to achieve the invariance, we instead did a model which we use an MLP, but in order to remove this translation symmetry, we just always center it by the like center mass of this image, right? We calculate the center mass of the image, and then we just center it on that, and then we feed it into the network. Both of these networks will have this translation invariance property. If we translate the image, we will get the same outputs. But the convnet will benefit from having the structure, which is, making the learning easier for each of these layers and making it easier to express functions. So both are valid approaches. And I think, it's a good start to do that, basically centering, or removing, redundant coordinates this way. But better is actually just going back to that original space, preserving the original structure of the problem, but encoding those symmetries, because then often these relationships are easier to learn. So that's what I would say with that. Although both are possible, it's just one it makes it easier to learn, and kind of the inductive biases are better matched to the problem.
So in that case, like what, if you don't mind elaborating just a tiny bit, like what, if you've already applied the symmetry, like what bias is left that you're not enforcing by doing this sort of centering approach? I guess I'm maybe still not totally clear.
So what, I guess one good example of this to keep in mind is where we're using these angular coordinates, right? Versus going back to the redundant Cartesian coordinates and then just enforcing constraints. So this is like the one that I was mentioning, right? And these are both equivalent representations of the state, right? Like we can represent them in either way and these dynamics. But by going to these angles, we're making the problem harder. We're basically twisting things up in a way by removing the degrees of freedom that makes it harder to learn. Whereas if we're going back to the Cartesian, kind of the original structure of the problem, and we're not messing with that, but instead just imposing whatever symmetries are there, then that's the thing that we're trying to learn is an easier, like it's an easier functional form. So I think that same principle holds for these other things like for an image centering or for your Mujoko environments and whatnot. Yeah, so I think that like this is an approach which just is making the thing that we're trying to learn, because of the coordinates that we're using, easier to express. And I think that is borne out by, you can run an MLP on an image which is centered, but it performs much, much worse. And so that has to do with more about the inductive biases and like how easy is it to express the function we want with those parameters in this setting versus this other setting. But yeah, it's a good question. And I should say also that in the, with the Mujoko environments, we didn't stray that far from kind of what people typically use. So we actually were still using these intrinsic, well, like the angle, this angle is defined relative to this other joint, right? So these, rather than the embeddings in 3D space. I think we could have done even better if we had done the embeddings in 3D space, but even there, we were just using those those, and there are still symmetries even there, right? The reflection symmetry, or swapping two joints, these kinds of symmetries. So I think both are possible, but I think preferably, the best thing is to retain the original structure of that problem and then just insert the symmetries rather than remove those symmetries from the structure of the problem and try to fit it in.
Thanks for the detailed answer.
So yeah, so I have another question. So I was intrigued by what you discovered about the symmetries in Majorco. Like there are weak symmetries as well as exact symmetries. So yeah, so do you think the realization of this will help with sim to real gaps, or when we transfer these neural networks to real life? And how should we do that?
Yeah, that's a good question. I don't have a whole lot of intuition for this. I optimistically would like to think that this is helpful in terms of, the more structure you have, the harder it is for you to fail in unexpected ways, or, for you to fail to generalize in unexpected ways. But I don't have a great intuition for this. And so I don't know. I mean, it's obviously not going to solve all the problems, but it's an interesting question. So I don't know the answer.
Okay.
Thank you for the talk and answering all of our questions. It looks like there's no more questions, and we've already kept you several minutes over time. So just wanted to thank you again.